This model represents a coupled pendulum. The two pendulums are free to spin to swing on ball bearings up here at the top, so there's very little friction. These are masses of iron, and the coupling spring ties the two pendulums together. And this is what we would call a strongly coupled system, in that it will have two distinctly different frequencies, and they're considerably apart in frequency. The first mode would be when they both swing together like this, and that will be the lowest frequency, the first mode of vibration. And the second mode of vibration would occur when the masses are moving in opposition to one another, and that one can be excited by giving each one the equivalent displacement corresponding to the eigenvector for that mode and released. So this one is considerably higher in frequency. Now, if we excite both modes at the same time, then we will see a beating effect between the frequencies, and it will be a very jerky motion in that the masses will alternate in stopping. It will appear the masses actually stop and then restart. And we can do this by just arbitrarily striking the shorter mass. And if you'll notice, the longer mass looks like it stops. Well, it does stop. And this represents the sum of two sinusoidal motions. Now, another example of this particular model is a weakly coupled pair of pendulums, in which the coupling spring is very weak. And by weakly coupled means that this will have two frequencies, maybe very close together, which means that there are some interesting beating effects. Again, the first mode of vibration would be both masses swinging together, and then the second mode of vibration would be when the masses swing in opposition. Then by exciting both modes at the same time, one can see a beating effect because we have two frequencies very close together. And you can note that this one stops, and then a few seconds later this one stops. And they'll take turns stopping, and those represent cancellations, or the point at which the two sine waves then add up to zero.